All right, so if you have your proofs out from here, I'll get these all on a separate page. Oh. We'll start with the first one. So again, every time we're doing a proof, we're writing out the question first. We're drawing a line to make sure that we don't move things from one side to the other. You're allowed to manipulate things on one side and manipulate things on the other side. And there's things you can change. I know I can change cotangent to 1 over tan or cos over sine. I can change tangent to sine over cos or 1 over cotangent. I can change cosecant to 1 over sine, and I can change secant to 1 over cos. So we have some options, and for some of them we have more than one option. Like for example, for cotangent, we can change it to cos over sine or 1 over tan. And both will work, but sometimes one is faster than the other. So how do we decide? Because I would sure like to know, if I'm making a decision which one's going to be faster, what I should choose first. In a question like this, one of the things you're going to do is you're going to look at both sides and sort of quickly in your head just imagine what are things that I can change to and look for some patterns. One thing that we've seen in some proofs so far is that if you could change everything to one single trig function, for example, if everything could be switched to tan, that's usually going to be the fastest way that you could prove it, if you can change it to just one. But when we look at this one, especially on the right-hand side, where I have cosecant, which can only be changed to 1 over sine, and secant that can only be changed to 1 over cos, I know that I can't change these all to one trig function. It's in those situations that it usually makes the most sense to change everything to sine and cosine, and then try to get a single fraction on both sides. So based on that, based on the fact that on this side, these are the only things that I can change to, and it's sine and cosine, when I go to cotangent, it's going to probably be the fastest method to change cotangent to cos over sine and tangent to sine theta over cos theta. Now my right-hand side is already a single fraction. It's 1 over sine theta times cos theta. Well, technically it was two fractions multiplied together, but it was pretty easy to multiply them. So that means on the right-hand side, I want to get the left-hand side also as a single fraction. So when looking at this, well, I'm adding fractions. Adding fractions, our rules are that I have to have a common denominator. So this one has to get multiplied by cos, and this one by sine and sine. And when I do that, I'll get a common denominator of sine theta cos theta, which at this point is making me happy because it's exactly the same as the other side. So I'm feeling like I'm getting close. On the top, I'm going to have cos times cos, which is cos squared, and sine times sine, which is sine squared. So now we've done the brunt of our work. We've got things changed to sine and cos, and we've got a single fraction on either side. But they're not quite equal yet. Can you see anything that you could do to either side that would help? What could you change? Yeah, cos squared plus sine squared, that's one of our Pythagorean identities. That's equal to 1. So you can change it to 1. And what do you know? We are done. The second proof. Cotangent cubed equals cotangent cosecant squared minus cotangent. So again, what I modeled in the last one for you guys was some pre-thinking. Okay? Sometimes you can just go into an identity and just start changing things. Just sort of like changing things as soon as you see them. Oh, cotangent. I'll change it to cos over sine. Or cotangent. I'll change it to 1 over tan right away. Because it's an identity and I should prove something. But I want you to take a step back, look at the whole thing, and do the same thing we thought about last time. We said, is there a way that I can change things so that it's all in one trig function? And we've got some new identities that we're working with now, right? We've got tan squared plus 1 equals secant squared, and we have cotangent squared plus 1 equals cosecant squared. And those are going to come important. And you should have all of your identities, even though they're on your formula sheet, you should have them like 98% memorized. Okay, you can have that little bit of doubt and say, ooh, what was it, plus 1 or minus 1? And you can look at your formula sheet to remember. But 98% memorized, because you need to be able to, when you get to a question like this, say cosecant squared and immediately go, I have a formula that has cosecant squared in it. If you don't have your formulas memorized, you'll just look blindly at this and then say, oh, I'll change everything to sine and cos. This one, if you change to sine and cos, will work. It will just take a lot longer. But here, I can change everything to cotangent. Because cosecant squared is cotangent squared plus 1. And so if I substitute that in, and any formula that's on your formula sheet you're allowed to use, well, now if I distribute it, I'm going to get cotangent cubed theta plus cotangent theta minus cotangent theta. Well, those will cancel out. And we're done. That's pretty quick, eh? What is that? All right, and the last one, as we're getting into some, yeah, I'll take this out. As we're getting into some more difficult proofs, we start adding some more strategies. Okay? So in this last one, it has tan squared and it has secant squared. And so the first thing that should be triggered for you is, oh, I have formulas that deal with that. So I could change tan squared to secant squared minus 1. Or I could change secant squared to tan squared plus 1. But we also have, on the left side, tan to the 4 theta minus secant to the 4 theta. And as we get into higher, more difficult identities, they're also going to require that you have good skills in factoring from grade 10 and grade 11. And so one of the strategies you're going to see and you're going to use in proofs is factoring. If you can see that something can be factored, it's usually helpful to factor it. And on the left-hand side, the tan to the 4 theta minus secant to the 4 theta is a type of factoring that you've done called difference of squares. How do we factor difference of squares? It's like difference of squares is like factoring x squared minus 9. Do you remember that? Where you would go x plus 3, x minus 3. So we have to you're probably pretty good at recognizing x squared minus 9. Well, now we have to recognize it with trig functions. We have something minus something, and this is tan squared squared minus secant squared squared. And so we can write it as a difference of squares. And here I can write tan squared theta, and secant squared theta secant squared theta. And one will be plus and one will be minus. What's nice about what we just did here is that we were able to now write both sides as tan squared and secant squared. But we still see on the left side that the left side is more complicated and bigger than the right side. So at this point, I'm going to look at tan squared plus secant squared, tan squared minus secant squared. And I'm going to look at the negative tan squared and the negative secant squared. And I'm going to look at the formula that has tan squared plus 1 equals secant squared. I'll write it off to the side here in a different color, just so that we can visualize it. Tan squared theta plus 1 equals secant squared theta. And I want you to move things around in that formula, and I want you to look at each of these three sets. Tan squared plus secant squared, tan squared minus secant squared, and negative tan squared minus secant squared. Of those three, if you played around with this equation by moving things over, is it possible ever to get tan squared plus secant squared on one side of that equation? Is it possible to ever get tan squared minus secant squared on one side? Or is it possible to get a minus tan squared and a minus secant squared on one side of this equation? Rearranging that, which of those three is possible? Because that's going to tell you what you need to do next. So we have to analyze the question that we have and say, could I rearrange that formula in green to get one of these sets that I have? So let's go through the first one. Can you rearrange that so you have tan squared plus secant squared? Yes or no? No. Because if I wanted the secant squared and the tan squared on the same side of my equation, what would I have to do to the secant squared? I'd have to subtract it to get it to this side, which tells me I can get a tan squared minus secant squared. So I'm going to take this second one, rewrite the first one, and I'm going to take, nice. I'm going to take the secant squared and substitute in that secant squared is equal to tan squared plus 1. And the reason why that's going to be nice is that's going to simplify that second factor. Tan squared minus tan squared is going to be 0. And you're going to have to distribute that negative as well. So after simplifying this, this whole thing is going to be negative 1. And now if I multiply this by a negative 1, I get negative tan squared theta minus secant squared theta. Nice. Okay, I'm going to give you some questions for this one. We're not going to work on them right now. 3, 5, 6II, 7II, and 9II.